over Los Angeles, California in the late 60s. One source of this thick, choking, smoky layer was the toxic emissions from vehicle exhausts. Over 2,000 tons of pollutants are emitted from vehicles in the Los Angeles basin every day. This cocktail of gases was often trapped over the city by the surrounding mountains. On particularly bad days, people's eyes streamed, and those with respiratory diseases became seriously ill. Most smog today is caused by a photochemical reaction between sunlight, unburned fuel, and oxides of nitrogen. Perhaps not surprisingly, California now operates the most stringent clean air legislation of anywhere in the world, and the air is cleaner now than at any time since records began. Although the motor car played a significant part in the pollution of air in Los Angeles, power stations and heavy industry were the chief culprits. This is true in Europe today, where vehicle exhaust emissions are only one of many sources of pollution. The EEC is now following the American lead, and a package of new regulations to limit the toxic emissions from motor vehicles is planned for the 1990s. So how will all this affect the way you service and work on Rover cars? Well, if you know the do's and don'ts and how the new systems work, you'll be okay. And that's what this program is designed to do. We're going to look at the exhaust gases, how they are formed, and the various ways of removing them, and any differences they make to working on the cars. So, what are the major pollutants in exhaust gas, and how do they get there? Petrol is made up largely of hydrogen and carbon, hence the chemical name hydrocarbon. In theory, when fuel is mixed with air in the correct proportions and ignited, the mixture burns quickly and completely. Burning is in fact a rapid oxidation. The oxygen in air unites with the carbon of the fuel to produce CO2, carbon dioxide, the gas responsible for putting bubbles in your beer. And the hydrogen unites with oxygen to form water. The nitrogen, which enters with the intake air, all being well, exits in the same form. So, the byproducts of complete combustion are carbon dioxide and water, both harmless. So where do the pollutants come from?
In theory, if you can completely burn a hydrocarbon, which is what petrol is, then you just get CO2 and water. The problem is we're trying to burn it very rapidly in an engine. We just have to think of the number of revs per minute that the engine's going at, and you've got to be burning it pretty rapidly. And bits of hydrocarbon get trapped in the crevices around the rings and where you screw the plugs in and various other things. So you can never really get to absolutely complete combustion. And so the things that are left are the result of that, and of the fact that you're using air to burn it rather than pure oxygen. So if you get to high enough temperatures, you start to convert some of the nitrogen into things like NOx, oxides of nitrogen, which are one of the main pollutants.
So the incomplete combustion, which happens in all engines, is the major cause of pollutants in the exhaust gases. Some fuel leaves the combustion chamber virtually untouched as hydrocarbons. Also, some of the carbon elements in fuel oxidize only partially and leave the combustion chamber as CO, carbon monoxide, the gas you measure when tuning an engine. And the third exhaust pollutant is oxides of nitrogen, known as NOx. This is formed when the normally inert nitrogen starts to burn at very high combustion temperatures. NOx gases have a tendency to react with hydrocarbons in the presence of sunlight. This reaction produces nitric acid, which contributes to the smog and acid rain problems. Carbon monoxide is a poisonous gas which is absorbed by the blood at the expense of oxygen. Hydrocarbons, such as petrol, can act as an irritant to the eyes and respiratory system. If you've ever used a meter like gas check, you'll know that emissions of hydrocarbons and carbon monoxide increase as the fuel mixture is enriched. This is because there isn't enough air in the mixture to burn all of the fuel. When we're talking about the motor vehicle and pollution, you can be forgiven for thinking that most of the different exhaust gases are poisonous to some degree, but you would be wrong. Remember, the main constituents of exhaust gas are harmless nitrogen, carbon dioxide, and water. Only 1% of total exhaust emissions are regulated pollutants, carbon monoxide making up the lion's share of this 1%. As you can imagine, these small levels of pollutants are extremely difficult to measure accurately. And when you're dealing with governments, you have to prove that your vehicle is clean under a variety of conditions, not just at idle. This emissions cell at Rover's test centre at Gaydon is where vehicles undergo a rigorous exhaust gas test cycle. This dynamometer is tuned to each vehicle with information on rolling resistance, vehicle weight, and even wind resistance to ensure the test results reflect actual driving conditions. There's even a fan to give the engine the correct amount of cooling air. The operator drives the vehicle through a specific test cycle, depending on the vehicle's market. The driver must match exactly the various speeds shown on the display, or the test is aborted. During the test, a continuous sample of exhaust gas is collected in a bag. The sample is then analysed and the results are calculated in grams per test. So we know the three major pollutants in exhaust gases are carbon monoxide, hydrocarbons, and nitrogen oxides. We know how they are produced, and we know what effects these gases have on us and the environment. Now, the big question is, how do we go about reducing them?
As regards the design, we have spent a lot of time and are continuing to spend time to develop the combustion chamber itself. Hydrocarbons and carbon monoxide are basically the results of inefficient combustion, and this is particularly relevant or prevalent at light load conditions on cold warm-up, etc. So we are spending a tremendous amount of time to make basically what comes out of the engine cleaner. In parallel with that, though, levels of nitrous oxides and CO2 will inevitably be there because they are the products of efficient combustion. And so you must develop catalyst technology, certainly to attack nitrous oxides. So we are working in cleaning up the base engine and then accepting that there will still be certain products that come out, maximising the effectiveness of the after-treatment. We should also say, however, carbon dioxide, which isn't currently legislated, is of environmental concern. And at the moment, there is no easy way to resolve that, because that is very much related to fuel economy. So one way we are attacking that is by making our vehicles even more fuel efficient than they currently are.
The drive to produce cleaner, more efficient engines has put Rover at the forefront of lean burn technology. Careful design of the engine, particularly the intake manifold and combustion chamber, means that smooth, powerful combustion can still be maintained at incredibly weak air-fuel ratios. By careful study of the combustion in the cylinder, the cleanest and most efficient combustion can be found. As a result, lean burn engines have very low emissions of carbon monoxide and hydrocarbons. The next step is to use a catalyst to remove any remaining pollutants. But what does a catalyst do and how does it work?
Well, that's the heart of one. That's the matrix or the core of a catalyst. It's made of ceramic and it's extruded, so you've got a large number of holes in it. There's 400 to the square inch. And because it's made of ceramic, it's got quite a good surface area. And you then coat it with another material to make it even bigger, so that something of that size has a surface area of around 2 or 3 football pitches. What you want it to do is to change 3 of the main things in exhaust gas. They're carbon monoxide and hydrocarbons, and you want to add oxygen to them effectively to make them into CO2. The other one is oxides of nitrogen, or NOx, and you want to take oxygen away from that to convert that into nitrogen. Now, given time, that happens naturally, but there isn't time in an exhaust pipe. So what a catalyst is something that speeds up reactions without actually changing itself. And the final coating on these things is platinum and other precious metals. And essentially, you can think of it as providing somewhere for the various chemicals to latch onto and get together. It will provide a surface where a carbon monoxide molecule, for instance, can sit on the surface of the platinum for a while. And if there happens to be an oxygen molecule sitting next to it, the two can get together and form CO2. And it does it for CO and for hydrocarbons, and at the same time it can do the opposite reaction of removing oxides of nitrogen.
So the long-term answer to reducing exhaust emissions still further involves using a catalytic converter. And the definition of a catalyst is something that promotes a reaction but doesn't itself become affected by that reaction. To enable the catalyst to work efficiently, a wash coat is applied to the ceramic. This increases the surface area by 7,000 times. And it's to this wash coat surface that the catalyst material is applied. The 3-way catalyst in common use has 2 tasks: oxidation and reduction. We'll cover the oxidation process first. To oxidize pollutants in the exhaust gas, the catalyst has a microscopic coating of platinum. 1 or 2 grams are all that's needed. When the engine is started, hot exhaust gases pass through the catalyst and it quickly heats up. As the catalyst reaches the required temperature, the platinum starts the reaction. Firstly, the carbon monoxide is oxidized and leaves the catalyst as carbon dioxide. The hydrocarbons are split into their base elements, hydrogen and carbon, and these too are oxidized. The carbon leaves the catalyst as carbon dioxide and the hydrogen as H2O, water. So the oxidation process converts the pollutant CO to carbon dioxide and HC to carbon dioxide and water. Now for the reduction task. The precious metal rhodium is used for the reduction of oxides of nitrogen in a 3-way catalyst. This strips the oxygen off the NOx and leaves harmless nitrogen. So, the catalyst is with us. But how effective is it? And is it here to stay?
We've made tremendous progress as compared with, say, 20 years ago. The understanding which we've gained of what goes on after the spark fires the mixture is light years from where we were previously. Nevertheless, there's still a lot that we need to understand, and we do know that with the way that requirements are becoming more and more stringent, there's no way that we can avoid catalysts and after-treatment in the rest of the vehicle. The application of catalysts implies a slightly higher level of back pressure in the exhaust system, but knowing that and understanding how exhaust systems work and how they interact with engines, there's no reason why we can't design the whole vehicle in such a way that any performance penalty is really quite minimal.
To sum up, the 3-way catalyst converts carbon monoxide, hydrocarbons and NOx into harmless carbon dioxide, water and nitrogen. So far, we've seen the catalyst working independently of the fuel system, with no interaction between the two. This is called open-loop control. Although an open-loop 3-way system works efficiently to give an impressive 50% drop in exhaust pollutant emissions, an even greater reduction can be achieved by closing the loop. A closed-loop catalyst system uses a sensor in the exhaust to help the engine management system maintain an exact fuel mixture. This fuel mixture provides the lowest total emissions of all three pollutants. If the air-fuel ratio is held at exactly 14.7 parts of air to 1 part of fuel by weight, the three-way catalyst has an astonishing conversion efficiency of all three pollutants in the order of 90%. The closed-loop fuel system is fitted to the Rover 820 and 827 catalyst options. Perhaps the most important component in a closed-loop system is this insignificant-looking object, an oxygen sensor. The sensor is positioned in the exhaust system forward of the catalyst. When the mixture is rich and the exhaust gas contains little oxygen, there is a large difference in oxygen content between the two sides of the sensor. This difference in content produces a voltage between the two surfaces of the sensor. So rich mixtures equal large sensor voltage, weak mixture equals low sensor voltage. The Fuel Injection Electronic Control Unit, or ECU, adjusts the air-fuel ratio depending on the level of voltage it receives. In this way, the air-fuel ratio is constantly updated to maintain the ideal mixture of 14.7 to 1. A rigorous test program ensures the exhaust gas catalyst will last for many thousands of miles. However, if the catalyst is abused, then it will soon lose some of its conversion efficiency. And if you're really careless, you can destroy the catalyst. So let's say that I'm particularly anti-ecology and want to destroy the catalyst in my car. What's the most effective way to do it?
The most important single item is the fact that with a catalyst, lead-free fuel is mandatory. You can only use lead-free. Leaded fuel will damage the catalyst. Apart from that, the visibility to the end customer is limited to a lower amount of service requirement.
It's going to be more difficult in many ways to measure the emissions at the tailpipe. In fact, you're very likely to have tappings before the catalyst because it's going to give you 90% or so reduction in emissions. So obviously the analysers that garages have at the moment just won't be able to cope with that. You're also going to need to be able to check out whether the catalyst is working.
And one thing in particular is they are very sensitive if the engine misfires. So it really is undesirable, in fact unacceptable, to run the engine with, for example, a spark plug lead disconnected, because what will end up is the catalyst will melt down and destruct.
With Rover catalyst-equipped cars, the fuel filler neck has a restrictor, and only the nozzle of a green pump will fit. Misfires cause large quantities of fuel to be dumped on a hot catalyst, and if not remedied, invariably lead to a catalyst melt. The odd misfire or cough as the engine starts doesn't cause a problem because the catalyst is cold and the amount of fuel passing through the exhaust is insignificant. Now, there are certain diagnostic testing procedures which involve isolating the ignition system of individual cylinders for short periods, like the cylinder power balance test. Is it okay to perform these tests on a catalyst-equipped car? The short answer is yes, but as they involve exposing the catalyst to small amounts of neat fuel, run the vehicle at idle for 5 minutes between tests to allow any excess fuel to burn off. The main thing is to avoid anything that will pump neat petrol through to the catalyst. Excessive petrol reaching the catalyst can start to burn the catalyst and cause a meltdown. For similar reasons, but to a lesser extent, push starting, toe starting, and prolonged cranking should be avoided. Excessive oil consumption, causing blue exhaust smoke, can leave carbon deposits on the catalyst which eventually plug it, leading to increased exhaust back pressure and lack of performance. On manual choke vehicles like the Mini, avoid running the car on choke for any longer than necessary, or this could also lead to carbon fouling of the catalyst. So there's a car with a catalyst in your workshop, needing a 12,000-mile service. Just what difference will a catalyst make to your job? We've just seen the consequences of misfires, and with this in mind, we must give the ignition system special attention. Make a thorough visual check of the system. Are there any loose or corroded connectors? Should that plug lead be routed quite like that? When you're changing a set of plugs, check the gaps. 5 thou can mean the difference between a plug that lasts the full 12,000 miles and one that doesn't. Check the plug KV using an engine analyzer. On a 214, there should be between 10 and 17 kV at idle. High readings could be due to incorrect plug gaps, a broken HT lead, or a worn rotor arm. Check it out. Now the tuning adjustments. Carry out preliminary checks on the system as normal. Are there any air leaks? Is the throttle cable lost motion gap correct? Don't forget the CO meter must be warmed, ready for use. Perform a 4-mile road test to warm the engine and transmission, and then you're ready for tuning. Connect microcheck and follow the on-screen instructions. When you're instructed to check the idle CO content, turn the engine off and remove the plug. Then connect the CO pipe to the sample tapping on the exhaust. Start the engine and increase the engine speed to 2,500 RPM for 10 seconds. The mixture can now be checked and adjusted using microcheck. The tuning data is the same as that for a car without a catalyst. If you made any adjustment to the mixture, don't forget to recheck the lost motion gap before disconnecting the equipment. Apply Bostik Never-Seez to the threads of the plug before refitting. It's important that you don't allow any of this compound to enter the exhaust and contaminate the catalyst. So that's the Rover 214. But how do you tune a car with a closed-loop system? The Rover 827, for instance. Well, the only area of tuning to check and adjust is the base idle speed. That doesn't mean that you can forget all the preliminary checks, though. Remember, the ignition system should receive special treatment on these cars. Make sure none of the HT leads are tangled, burnt or split. Before tuning, turn the ignition on and check the red diagnostic light on the fuel ECU. If this is flashing or permanently lit, do not attempt to set the base idle. A complete breakdown of ECU fault codes and their corrective sequences is contained in the Rover 827 Electrical Fault Finding Manual. When you are satisfied everything is okay, warm the engine and transmission on a road test and you're ready for tuning. On returning from the road test, check the yellow LED on the fuel ECU with the engine idling. If it's flashing, you'll need to turn the throttle body adjusting screw clockwise, and if it's continuously lit, anti-clockwise. It's important that you turn the screw in small increments, waiting for a response each time until the light goes out, and that's it. Similarly, with the Rover 820 MPI catalyst cars, no adjustment of idle mixture is possible, and tuning is restricted to setting the base idle speed. Now, a few points to help you diagnose faults on catalysts. First, before you even think of checking the catalyst, you must ensure the engine is running cleanly. How you do this depends on whether the car is an open-loop or closed-loop system. On open-loop cars, warm the vehicle on a road test and check CO content at the sample tapping upstream of the catalyst. Make sure this is okay before proceeding. With closed-loop cars, there is no tapping in the exhaust upstream of the catalyst. So how do we make sure the fuel mixture is correct? Well, remember that closed-loop systems control fueling to an exact ratio. So to determine whether air-fuel ratio is correct, all we have to do is determine whether closed-loop control is taking place. With a Rover 827, perform a road test, then check the red diagnostic light. If the red LED isn't flashing or permanently lit, then you know that the closed-loop control is working. With the 820, you also need to warm it up on the road. As soon as you return, connect a voltmeter using the special T-in harness. Increase speed to 3,000 RPM for 30 seconds. Now, if the closed-loop system is okay, the meter reading will swing regularly between 0.2 and 0.8 volts. So we know the engine's running correctly. But how do we check the catalyst? Perform a brisk road test and directly on return, check CO content at the tailpipe. High emissions indicate a faulty catalyst. The booklet details the readings to expect. Before condemning the catalyst, drive the vehicle for at least 20 minutes at motorway speeds to burn off any carbon deposits that may have accumulated. If the catalyst still appears dead after this, change it. Be very careful when diagnosing catalyst faults. High tailpipe emissions can result if the exhaust gas is simply too dirty to clean. So always make sure the engine is correctly tuned first. This is what a new catalyst looks like, and this one's plugged. Obviously, before you replace a catalyst, you must first find the cause of the initial blockage. A blocked catalyst can cause performance and economy problems, but problems like this are extremely rare. There we are. Not so much a definitive guide to the diagnosis of faults on catalyst-equipped cars as a few hints and tips to help you. More information is contained in the booklet and, of course, the fault diagnosis manuals. To round up, let's take another look at the main points of the program. CO, hydrocarbons and NOx are the main regulated pollutants emitted from car exhausts. But these pollutants make up only 1% of total exhaust emissions. The catalyst converts CO to carbon dioxide and hydrocarbons to carbon dioxide and water, and also removes the oxygen from NOx, leaving only harmless nitrogen. The three-way catalyst achieves greater conversion of pollutant gases if used in conjunction with a closed-loop fuel injection system. A catalyst can be ruined if the car has a persistent misfire, allowing fuel to reach the catalyst. On cars with an open-loop catalyst system, exhaust gas CO content must be checked at a special tapping, not on the tailpipe. Tuning of vehicles with closed-loop systems is restricted to setting the base idle speed. The most important rule to follow when diagnosing faults on a catalyst vehicle is change the catalyst only as a last resort when every other possible cause has been thoroughly explored. And above all, only unleaded fuel must be used. Finally, the booklet contains a host of useful information to help you and a quiz to test your knowledge. Send your answer sheets in after you have done the quiz. The problem of pollution affects all of us. The use of unleaded fuel and catalysts helps to protect our environment. If you understand how catalysts operate and how to make sure they keep operating efficiently, you can prevent pollution and provide a safer, cleaner future for us all.